Welcome to a brief video describing the results of FPath Experiment 010. FPath is my project name for experiments on the Feynman Path to Nanotechnology. And what is the Feynman Path to Nanotechnology? Well, it is the idea that you have large machines make smaller machines, which in turn make smaller machines, and so on until you reach the point where you can reliably move atoms about at the nanometer scale. Of course, the FPath project is nowhere near that yet. It is now operating on the scale of millimeters. This experiment documents how the FPath project has achieved submillimeter movement using cheap off-the-shelf actuators as an XY stage and closed-loop feedback to compensate for the appalling amount of backlash and slop that these components display. On the screen, you can see an enlarged view of a segment of nichrome wire, which, for this experiment, forms the tool being moved about. It is 0.1 of a millimeter in diameter, a nominal 100 microns, or approximately the width of a human hair. The Walnut control software is moving it about under the control of manual user keyboard instruction. But we are getting ahead of ourselves. Let's begin at the beginning and provide some background. I assure you, there is much more interesting stuff to come than just video of me moving a tiny bit of wire about. In order to get X and Y movement, you need something to actually do the movement. Since the FPath project is all about getting small machines to make even smaller machines, I decided as a first pass to try and make the XY stage as small and as cheaply as possible. So, I took two of the medium stepper motor assemblies evaluated in experiment 008 and some Lego bricks and made them into a XY stage. As a recap, these motorized actuators have a theoretical per-step movement of about 2.5 microns. This is entirely due to the planetary gear coupled to the motor. You can see a red arrow pointing to the planetary gear. The planetary gear also drops the gear ratio so much that this little device exhibits quite a useful amount of torque for its size. There is also a parallel rail running alongside the lead screw that keeps the carriage straight and level. This makes implementation much simpler. You can see that the stepper motors are built into a Lego structure and that the whole thing is not really very large, probably 25 by 35 by 25 millimeters. It is larger than I would like, but it forms a pretty useful starting point. I don't want to go into how to build a Lego XY stage in this video. I will produce a separate video on that topic if there is any interest. However, just realize it is not all that amazing. Essentially, it is just two inexpensive stepper actuators fastened to each other at right angles with some Lego bricks around them to help stop the wobble. I've extended the concept into the third dimension, producing a z-axis, but that is a topic for another experiment. Just for the record, here is a shot of the first prototype of this XY stage. As you can see, I was more interested in getting the sizing and spacings right than on aesthetics. The second stage shown here is the one currently in use for this experiment. The third stage has a prototype Z-axis fitted to the tool head. I'm not really sure I like this design, but I did use red Legos for the bearing tiles, so it does look kind of snazzy. Also, the use of Lego bricks as cable trays for the stepper wires complicates the build process considerably. You'll note that there are 4 sets of wires out the back. I took the opportunity to run another cable loom up to the tool head for sensors and such. You can see it attached on the top rail in the form of the smallest, lightest terminal block I could find. Here is an image of the XY stage mounted on the experimental bed. As is my habit, Lego is used throughout, and it does a nice job of keeping things square while still letting me firmly position parts to a reasonable tolerance. The part of the stage that moves, the tool head, is a 1x3 white Lego tile with a bit of 100 micron wire glued to it and protruding from the end. The work surface is a 1x2 Lego tile mounted on a small stack of Lego bricks. Because the build of the XY stage is carefully designed to preserve an integral number of Lego unit heights, both the tool head and work surface are nicely level with each other in the vertical direction, and I do not need to worry about that very much, even though I do not have a Z height adjust operational yet. Returning to a larger scale view, you can see that if the motors in the XY stage move, then the tool head will also be moved. Because of the planetary gear, the bottom motor of these El Cheapo actuators, the Y-axis, actually has enough torque to move the Lego bricks, which are pretty light, and also the mass of the X-axis motor. Enough of the background. Let's get on with the experiment. We insert the bed into the old RepRap Mendel, which serves as the FPath experimental platform. Then we drop the Mendel Z-axis down in order to get a nice enlarged view of the contents of our work surface. The first thing we need to do is calibrate the display. The way I'm going to do this is by using an object of known dimensions along with the tools demonstrated in experiment 009. The object of known dimensions in this case is a 0402 surface mount resistor. These minuscule little things are 1 millimeter by half a millimeter by definition. In other words, 1,000 microns by 500 microns. Online, I purchased a sample book stuffed full of tapes of these tiny little things for a quite nominal cost, and now I have more 0402 SMD resistors than I will ever need in several lifetimes. I actually pulled the data sheet for these resistors from the manufacturer, and the dimensions are supposed to have a tolerance of plus or minus 50 microns. Normally, I would take such declarations with a grain of salt, but since these resistors have to run through very expensive pick-and-place machines, I think they are probably all pretty close to spec. Anything out of size is probably going to mess up these machines big time and hence enrage the PCB manufacturers. The upshot is that I glue a 0402 resistor to the work surface with the long part horizontal and drop the microscope so the case fills most of the screen. Knowing that side of the resistor is 1000 microns, I can easily use tools in the Walnut software to calibrate off of that. It is my belief that I'm probably not too far off in scale. In the interest of time, I'm not going to show you the calibration process. If you are interested, you can see how it's done by looking at the video for experiment 009. Simply moving the bed of the RepRap Mendel forward brings the wire attached to the tool head into view. What you are seeing here is the work surface with the wire resting on it. At this magnification, the tool head the wire is actually glued to is out of shot at the bottom. Of course, the 0402 resistor is out of frame at the top. Let's put the XY stage through its paces. We will move this bit of wire about and see what kind of accuracy we might get. But first, it would be nice to have some targets. As a note, in the following demonstrations, I'm going to jump between a view recorded by the Walnut software, which shows only the USB microscope image, and a view of the Walnut software taken by some screen grab software. Since we are calibrated, note the calibration bar now at the bottom of the image panel, I can add a grid to the display. Here I am overlaying a 5x5 array of yellow crosses at 200 micron spacing to the image. The ability to manually move the tool head about has been added to the Walnut software. I'm using the standard W, A, S, and D keys so beloved of computer gamers for this purpose. In other words, the A key moves the tool head to the left and the D key moves the tool head to the right, and so on. All the speeds are settable. I am using the small indent at the top of the wire as an aiming point. As the WASD keys move the tool head about, you can see that with a bit of nudging and shoving, the dot at the end of the wire can be positioned with both considerable accuracy and precision. Now, I know what you're thinking. Hey, old dude, you're repeating yourself. Accuracy and precision are the same thing. Well, no, they are not. For those of you that are not familiar with the difference, I will try to explain. Say you've built a machine that throws darts at a board. You set it off and the dart lands dead center. You might claim that your machine is quite accurate. If instead your dart landed somewhere else, on a double 6 for example, you would not be best pleased. However, if you set off 2 more darts and they all landed on the double 6 as well, you could say that your device was quite precise. Precision is all about repeatability. Accuracy is about absolutes. This is why, when shooting a rifle, a nice tight group is much more sought after than hitting the target dead center. After all, the sights can always be adjusted to move the grouping wherever you wish. But I digress. Back to the matter at hand. It gets a bit tedious to move the tool head manually, so an automated mode was added to the Walnut software to move the tool head to a target point. If we are going to move source to target, then we need a definitive source point. Accordingly, a bit of image recognition code was developed to locate a consistent point on the end of the wire. Here is the interface to that code. There are lots of parameters, and I won't go into them all now, but suffice it to say, if I turn on horizontal and vertical lines, we can see the image recognition code has found the end of the wire. Here I have the lines adjusted so they cross on the same indent we used earlier with the WASD keys. I can place a helpful red dot on this intersection. I will also turn off the lines. They just get in the way. However, do remember that they are being used to identify a consistent point on the end of the wire for each frame inbound from the USB microscope, 30 frames per second in this case. This means as the wire moves, the red dot will change position in real time. I'll not go into the image recognition here for time reasons. I will do another video specifically about that in the future. In the meantime, the Walnut code is open source, so you can always just pull the repo and have a look at it if you wish. So, the red dot gives us our source. We also need a target. To do this, I will simply click with the mouse on the screen. The Walnut software knows perfectly well where we clicked. However, for our use, I will have the software mark the click point with a small green circle. Thus, to move a source to a target, all we need to do is move the red dot onto the green dot. I will activate this mode here. As you can see, it is possible to move the tool head around in an automated way just by clicking on the screen and dropping a green dot. I call this auto assist mode. Auto assist mode is much faster than moving the tool head manually. Also, it does demonstrate some interesting things. Note that sometimes there is overshoot and the tool head has to go back and wiggle its way to the target. Remember, the grid spacing here is 200 microns, so the overshoot distances are on the order of 10 microns or so. Given that the motors and support infrastructure are not of good quality, I suppose the crappy little XY stage can be forgiven a little bit of adjustment. This will just have to be expected and coped with in future experiments. The point is that it gets to the target in the end. We can develop methods of work that take that into account. Another thing is that when the target dot is at a 45-degree angle from the source, you expect the red dot to go straight there. Yet sometimes it takes a much more circuitous route. You can see a particularly egregious example of that on the display now. The thing is, both motors are actually moving. It's just that because one axis changed direction, the closed-loop feedback code is busy sucking up a whole bunch of backlash, so there is only the other axis physically moving. In other words, both axis motors are spinning, but only one is moving and the other is frantically consuming slop and play in the gearing until it too begins to move. Once you have the ability to move a source point to a target point, you can begin to do a lot of interesting things with it. It all depends on how you choose your target. What if, instead of being told the target point by a mouse click, we write an algorithm that finds the closest green pixel to the red dot? It doesn't really matter how we get our target point. The move source to target behavior is compelled to move the red dot there just the same. Furthermore, what if we dissolve the green point once the red point gets within a defined proximity to it? Then the algorithm will be forced to find the next best closest green point, and the red dot will immediately head there instead. Think about it. We get path-following behavior as a kind of emergent property of a simple move source-to-target behavior. I originally demonstrated this back in experiment 003, but it bears testing out here on the sub-millimeter level. Say we decide to draw a shape on the screen. Here, a 50-pixel green circle. We activate the code that moves the red dot to the nearest green pixel. We can see the tool head move towards the target. However, once the red dot is within 6 pixels of the green, the code simply renders any green pixels transparent. You can see this happening, and the path-following behavior emerges from these simple actions. Well, that's pretty cool. As they say in the old country, it's the bee's knees. While we are on the subject of following a path, let's see if we can extend it some more. Experiment 003 demonstrated the loading of a file with an image of an arbitrary path and having the tool follow that, so I won't show it again. But what if when we move the tool head, either manually or by auto assist, we record the path it took? Paths are paths, so if we can follow one forward, we can just as well follow it back. Here is an example. The auto assist is moving the red dot around as before, but we have enabled some code to lay down a cyan-colored tracker trace. Once we get to the stop point, we have a nice trail showing where our path was. Okay, it's not that great a path. In this case, the path does look a bit erratic since the cyan pixel is laid down wherever the red dot appears, and the red dot jumps about a bit due to imperfections in the image recognition algorithm. However, you get the idea. Ultimately, as we shall see, it does not matter all that much. Just as before, we can move towards the target pixel and yet remove the target pixel just before we reach it. However, in this case, instead of seeking a green pixel as a target, we tell the algorithm to move towards the next cyan pixel. We follow the exact same path back to the start. Think about the implications of this. If the tool head moves, however caused, and the other agents in the system react to the environment, perhaps avoiding an obstacle, we can have a real record of the tool head's movements, not just an internal model. In order to repeat the movement, the code only needs to follow the path backwards and forwards. It does not need to know what triggers modified the path, just that the path exists as it is. I can see how this might be useful for lots of things, not the least of which is implementing repetitive behaviors. Note that I have named this graphical methodology graphical stigmergy. Stigmergy is the technique ants use to signal to each other. Basically, they modify the environment with sense, and other ants react to it. And you get all sorts of complex emergent behaviors from what are really quite simple creatures individually. Here it is done with pixels, but the effect is the same. For the record, here is a quick view of the chain of stereoelectronics modules used in this experiment. From left to right, there are a power supply module for 3.3 and 5 volts, a BeagleBone Black breakout module, the Walnut client software runs on this. After that, there is a small fan-out board to tie the various grounds together, and a switch to stop all stepper motor power. 2 more fan-out boards follow. These split the logic and stepper power supplies for the 3 low-voltage stepper motor drivers on the right. Well, that's all for now. I just thought you might be interested in how closed-loop feedback can enable low-cost hardware to move a tool at the submillimeter scale. I also thought I would demonstrate how those movements can be automated and extended into some interesting path-following behaviors. Thank you for watching, and see you next time.